Hey everybody, we are now at that point where we can interpret our independent sample's t-value. We're going to go through every step here from after having all of our results so that we can see how we apply all of this knowledge to actually get to the final interpretation. If you've not been following these videos in sequence, I'm going to have to catch you up just a little bit, but we'll do that quickly. So I gave a scenario several videos ago in which we had an independent variable of two versions of a pamphlet, okay? They're both on fire safety, but they were presented in different ways. We called one of them a red pamphlet version and the other is a green pamphlet version. Okay, so that's our independent variable. There are only two options. We treated the red pamphlet as group 1 and the green pamphlet as group 2. Doesn't matter which you pick, you just need to keep track. Okay, the dependent variable is of course a quiz on fire safety. So in other words, we randomly selected these people, we randomly assigned them to receive either the red pamphlet or the green pamphlet. Then after they read through the pamphlet, we gave them a quiz on fire safety and they all received the same quiz. There was no interaction of anybody in between, no relationship of anybody in either group, and so we can treat these as independent samples. We did the math a couple of videos ago and we found that our t-value is negative 2.62. We also found that we have 11 degrees of freedom. Again, if you're not familiar with how to get to that point, please go back and view those videos. Okay, and additionally, we learned in our last video that because we didn't suspect which pamphlet would do better, we didn't have reason to believe that it would be the red one versus the green one or vice versa. We treat this using the two-tailed test criterion, I should say. Okay, and so now to figure out what we do next is we look at Appendix B because we need to find out what value of t would be statistically significant. So let me show you how to do that. Again, we pull up Appendix B in my textbook. If you don't have my textbook, just find any kind of distribution. You should have one in your textbook. It may not be Appendix B, but it'll be a t distribution, or it might be called the critical values of t, something like that. You can also Google that information, and there are lots of options out there. Hopefully they're all accurate. If when in doubt, buy my textbook, of course. Says the guy who wrote the textbook. Okay, so as we can see here, we're just using the two-tailed test criterion, right? Only the left side of Appendix B. The right side covers the one-tailed version, so we're going to leave that out for this particular issue here. Now you'll notice here these three columns that have this corresponding value here of 0.05, 0.01, and 0.001. That's the proportion of the tail that goes beyond what is called the critical value. And these values here are critical values. This will make a little bit more sense as we apply this. What this means is it's essentially the exact same thing as the p-value. Okay, the p-value, as we said, is the probability that you would find this value if the independent variable has no effect on the dependent variable. And of course, if the independent variable has no effect on the dependent variable, we don't want to find a value like this because that would mean that we're making a mistake. So this is why we can go ahead and say that there is an effect because these are rare values. What it's saying is, for example, if you had a test with 3 degrees of freedom, you would expect a t-value of 3.182 to occur only 5% of the time or less. Okay, so that's where we can get to this point, right? So we generally in statistics, especially social sciences research, we start with the critical value, the p-value of 0.05. So in other words, we want to start out with a 5% chance of making a mistake and no higher. That's essentially what this is. Now, you'll notice that we need to find in this last column, this column over here, I guess that's the first column, we need to find the criteria for the critical value for a test with our characteristics. We had 11 degrees of freedom, and so as you can see here, we don't have an 11 row. All we do is turn the page, of course. So I'm going to do that here. So as we can see, this page starts with 11 degrees of freedom. That's all we're interested in for our test because our test did not have 12 degrees of freedom. It did not have 11 degrees of freedom. So we're just interested in this row. As you can see, if our threshold, we'll say highest threshold of 0.05, in other words, we need this value to occur no more than 5% of the time, then we're starting with a value of 2.201. In other words, what we're learning is if we have 11 degrees of freedom, we wouldn't expect the value of 2.201 to occur unless the independent variable really had an influence on the dependent variable. Okay, so that is what we need. Now, what this is essentially saying is, because this is a two-tailed test, it's saying this is the distance away from zero that our critical value is. So you can treat it as if it's a plus or minus 2.201. Let's take a look at our distribution of t-values to see what this actually is saying. So here's our distribution of t-values. You remember this from a few lessons ago, right? So essentially what we're saying is these are all sorts of t-values that are fair. They're not super uncommon, right? We expect to see a lot of t-values occur, even if our independent variable has no impact on our dependent variable, if we have 11 degrees of freedom. But now, since we looked up that critical value, we can place this value at the threshold. So in other words, what we're saying is, although we expect to see lots of t-values 95% of the time, any t-value beyond 2 or equal to or beyond 2.201 is unusual. It's unusual enough that we see it less than, well, equal to or less than 5% of the time. Okay, so because this is a two-tailed test criterion, we can put it as a negative 2.201 down here on the low end, or a positive 2.201 at the high end. So any value that goes outside of that range, negative 2.201 or positive 2.201, is statistically significant. Statistically significant just means we wouldn't expect to see it at least 5% of the time or more unless there really is an impact of the independent variable on the dependent variable. Okay, let's take another look here. So we had a t-value that we calculated using our data of negative 2.62. So what I'm saying then is this: if that falls right here, that's lower than negative 2.201. Negative 2.62 is lower than 2.2, negative 2.2, right? And so it is falling outside of that realm of rather boring t-values, or at least not statistically significant t-values, and it is in the realm of interesting or statistically significant t-values. So negative 2.62 is statistically significant in a test with 11 degrees of freedom. Yes, another way to think about this is it's farther away from 0 than our critical value of 2.201, because the table just gives us the positive version, but all that's talking about is distance away from 0. Okay, so negative 2.62 is farther away from 0 than negative 2.201. Now let's put it in a paragraph that people can hopefully understand, especially if we're publishing this research or sharing it with other people. To kind of wrap it all up, what I'm saying is we found a meaningful difference in our fire safety quiz scores between the group who received the green pamphlet versus the red pamphlet. Therefore, because we found a meaningful or statistically significant difference, we can reject our null hypothesis. We can reject that default hypothesis that said there was no difference, because now we have strong evidence to suggest that there is a difference. Okay, and so we can do that also with less than a 5% likelihood of committing a type 1 error. If our computed t-value was negative 2.201, I would say we have a approximately 5% chance of committing a type 1 error by rejecting the null hypothesis. All right. In other words, it's like saying if I were to say that there is no difference here, I'm sorry. If I am incorrectly rejecting my null hypothesis, there's a 5% chance that I'm wrong about that, right? That's essentially what you're saying. Okay, to get a little more specific, I can also say that it was the people who used the green pamphlet who did better on average in their fire safety quiz score than the people in the red group. Okay, I'll show you in a second why I know that, right? Because some of you are going, whoa, how do you know which group did better? And I'll show you in just a second. This is a nice way that we summarize this in APA format. A t-test can be summarized in this following manner. You indicate that it is a t. In fact, I would probably say independent samples t to be specific here, unless that's in the paragraph anyway, with 11 degrees of freedom, and this is the actual value of the t we calculated. And then this is our p-value, or our likelihood of committing a type 1 error. So I'm saying our probability of committing a type 1 error by rejecting our null hypothesis is less than 5% in this case, because it was also a bigger value that we calculated than the critical value. If they were the same value, I would say p equals 0.05. Okay. So in other words, I could say the difference that we found in the quiz scores between the red pamphlet group and the green pamphlet group was big enough that I can say there probably was an effect of which pamphlet they got on their actual quiz scores. So what we now need to do as a research, I say let's give everybody the green pamphlet because that seems to help them with their fire safety knowledge. Now, let's take a look at how I knew that it was the green pamphlet group. First of all, if it's a negative t-value, you therefore know that the second group had a larger mean than the first group. And because I treated the green pamphlet group as the second group, that means the green pamphlet group did better than the red pamphlet group, because a small number minus a larger number equals a negative number, okay? If you're still not sure or want to double check, you can go back and find your math. You can look on the numerator of the t equation as you computed it, or you could just go back and find those means that we computed. So we did this several videos ago, right? The red pamphlet group had a mean of 4.57 points on the fire safety quiz score, and the green pamphlet group had a mean of 6.83 on average on that fire safety quiz score. 6.83 is of course larger than 4.57. I already knew that. However, the t-test showed us that not only is it higher, it's statistically significantly higher. In other words, it's meaningfully higher. This is not an accidental difference, for example, is a nice way to think about that. Okay, let's wrap all this up by showing you a little cheat sheet that I find is helpful, because there's a lot of steps to a t-test, and so I just want to see if we can clarify this a little bit. First, when you've got your scenario for a t-test, you clearly state what are your null and alternative hypotheses. We have a whole video on that. You can check that out. Then you do the math to obtain your t-value. Again, I've shown you how to do that. Make sure that you're using the correct equation, whether it's independent samples or dependent samples. We did only the example using an independent samples so far. Maybe in the future I'll add one that does a dependent samples. Then you need to find the critical value using your degrees of freedom. So again, you use the degrees of freedom that you calculate. It's just n1 plus n2 minus 2. And then you find out your critical t-value using that appendix B. Then you test, is your value that you calculated bigger or smaller than, at least in absolute value, the critical t-value you just looked up using the one or two-tailed test criteria? If it is larger than the critical value, then you have statistical significance, or if it's at least farther away from 0 than the critical value, I'll say that, to account for those negative values, then it was statistically significant. You reject the null hypothesis, and you can say you found a meaningful difference. All of those things mean the same thing, okay? They all go together, I'll say. There's never a circumstance where you would reject the null hypothesis but not have found a statistically significant difference. That wouldn't be real. If it is not bigger than the critical value or farther away from 0 than the critical value, then your p-value is greater than 0.05. and it was not statistically significant. You retain the null hypothesis and did not find a difference. One little note here, this is actually greater than or equal to, I'll say. I'm sorry, less than or equal to 0.05, because it is still statistically significant if it's equal to 0.05. That's a little note there. And then you write a clear summary of what you found, just like I showed you. Okay. That's it for the t-test so far. We've got a few other things that we can now do as sort of follow-ups to the t-value. So I'll walk you through those interesting steps here in the next couple of videos. I'll see you then.